Let's look at another example of a triple integral that is kind of awkward in Cartesian coordinates. So this is going to be the triple integral of x squared over the unit ball x squared plus y squared plus z squared less than or equal to 1. So this is just everything inside of the unit sphere. Right, that's going to look like something like this, right? So this is the region that we're integrating over. So this is going to be triple integral of r over the region r, integral of x dv. And if you think about describing this in Cartesian coordinates, let's see, we have to choose an order. And let's do, I guess, reverse alphabetical for no real reason. Because of the symmetry of the shape, it turns out to be just as bad in any other order. So what x coordinates does this region touch? Well, it goes from -1 to 1, because it's the unit ball. What y coordinates does it touch? Well, if you look at, if you take a slice at a certain position, you get a circle, right, for that slice. And what y coordinates does the circle touch? Well, it actually depends on the x coordinate, because the radius of the circle gets smaller as you move further to the right on this thing. But the way that y depends on x is, well, I'm sorry, I've drawn this. So let's say the z-axis is coming out towards us, so that I can not redraw this picture. This top curve is the graph of the radius of this circle with respect to x. So this is a unit circle, and that means that, so the radius of the circle is going to, or what am I trying to say? The y along for this, the radius of the circle is, right, x squared. This circle is x squared plus y squared. Sorry, got myself a little bit tied up. Okay, so this circle here that this top curve is a part of is x squared plus y squared equals 1. Okay, so if we solve this for y, we get y equals plus or minus the square root of 1 minus x squared. There we go. So the y coordinates that this cross section touches is these y coordinates. So from minus square root of 1 minus x squared up to plus the square root of 1 minus x squared. Okay, so that's kind of ugly as bounds. And then on this particular circle, what z coordinates does this particular circle touch? So on this, right, I have my y-axis going this way and my z-axis going this way, because z is coming out of the screen in this picture. So the z coordinates depend on y like this. So remember, the radius of this circle. So, well, I guess the easiest way to get at the z coordinates that this touches is just to recognize that we're going across this part of the sphere. So what bounds the endpoints of this line segment is the sphere itself, and the sphere is x squared plus y squared plus z squared equals 1. And then we can solve this for z. Z is plus or minus the square root of 1 minus x squared minus y squared. So this goes from minus the square root of 1 minus x squared minus y squared up to plus the square root of 1 minus x squared minus y squared. Okay, so if we write the integral this way, the bounds are really messy, right? The integrand is fine, but the bounds are really messy, and that's going to make this kind of difficult to integrate, even though it seems like it shouldn't be so bad, because the sphere is such a nice shape, and this integrand is certainly no problem. Oh, I'm missing a squared here. And you know, the problem is that right? We have this nice symmetrical shape, a sphere, but we aren't taking advantage of that nice symmetrical shape in any way, right? It would be nicest to use some kind of coordinate system where the distance from the origin is one of your coordinates, so that writing down the sphere would just be saying, well, the distance from the origin is less than or equal to 1. So what we need to make this a little bit easier is to use a coordinate system where distance to the origin is a coordinate, is one of our coordinates. Okay, so let's see how that would work out. All right, so we have a point in 3D space, and we're going to use the distance from the origin as one of our coordinate systems. So this looks like a p, but this is actually a rho. It's a lowercase Greek r, essentially. If we're going to use distance from the origin as one of our coordinates, well, the other nice coordinates to use in that situation are this angle down here, which we'll call theta, and the angle down from the positive z-axis, which we'll call phi. This is a Greek lowercase f, essentially. This theta is the same theta as in polar coordinates. Notice that in the xy plane, we're actually just using polar coordinates because we have this distance r and an angle theta, but the difference now is that we aren't going to use the coordinate z. Right? If we used r, theta, and z, that would just be cylindrical coordinates. Instead, we want to use rho. So what we need to do is write x, y, and z in terms of rho. And let's start by writing r in terms of rho, phi, and theta. So one important thing to notice in this setup is that because the z-axis and this vertical line segment are parallel, and this angle down here is phi, that means this angle up here is also phi. Okay. And we have this right triangle here, so we can use right angle trig on this right triangle to figure out what r is. R is the hypotenuse, which is rho, times the cosine of phi, because this side r is opposite phi. Also, while we're at it, we can write z in terms of rho and phi, because z is the other side of this right triangle. So it's the hypotenuse, rho, times the sine of phi. I have these backwards. This one's cosine, and this one's sine. There we go. Okay. Well, for x and y, in the xy plane, if we look at r and theta, x and y, r and theta, that's just Cartesian coordinates and polar coordinates in the xy plane. So x is r cosine theta, and y is r sine theta. But we have r in terms of rho and phi, so we can write x as rho cosine theta sine phi, and we can write y as rho sine theta sine phi. Okay, so we have these three expressions that tell us x, y, and z in terms of rho, theta, and phi. This coordinate system, because if we set rho equal to a constant, we get a sphere. This coordinate system is called spherical coordinates. Okay. It's a good exercise to figure out how to go the other way. So we have written x, y, and z in terms of rho, theta, and phi. It's a good exercise to figure out how to express rho, theta, and phi in terms of x, y, and z. I'll let you work out the details for theta and phi, but let's actually write what rho is in terms of x, y, and z. Well, remember, rho is just the distance from the origin, so that's in 3D, the distance from the origin is the square root of x squared plus y squared plus z squared. Okay, so rho is the square root of x squared plus y squared plus z squared. So if you want to square both sides, you could say rho squared is x squared plus y squared plus z squared. So if you see an x squared plus y squared plus z squared, that's kind of a sign that maybe spherical coordinates would be a good idea. To get a little more comfortable with this coordinate system, let's look at some common shapes that show up when you're using spherical coordinates. So first, let's sketch the surface rho equals 3. Well, remember, rho is the distance to the origin. So the points that satisfy rho equals 3, these are going to be all the points that are 3 units from the origin. Well, that's just a sphere, right? That's the definition of a sphere with radius 3. Okay, so this doesn't quite look spherical because I'm having a bad drawing day, but this is a sphere of radius 3. Right? So rho equals 3, that gives you a sphere. You can see rho equals any constant is going to give you a sphere, just with different radii. All right. So that's what happens if we set the rho coordinate equal to a constant. Let's see what happens when we set the theta coordinate equal to a constant. For example, theta equals pi over 4. So let me draw some coordinate axes so that we can situate this in space. So remember, theta is the same theta as polar coordinates in the xy plane. So theta equals pi over 4. That's going to be this right here. Right? So there, theta is pi over 4. But remember, if you go up and down, all of those points directly above and below this line segment will also have the same theta value, because right, theta is always measuring the horizontal angle between the positive x direction and your point. So all of these points will have theta equal to pi over 4. So this is a vertical plane, essentially. It's a diagonal vertical plane, right? It's the plane sitting above and below this line in the xy plane. Right, so theta equals a constant gives you vertical planes through the origin. So that's what happens if you set theta equal to a constant. Let's see what surfaces we get by setting phi equal to a constant. This time I'm only going to draw the z-axis, just because otherwise the diagram is going to get messy. So remember, what phi measures is the angle down from the positive z-axis. So we need to go from the positive z-axis down an angle pi over 3. Right, so there's one of our points. But right, we need to go down from the positive z-axis pi over 3 in every direction. So this direction and right, this direction and back. Right. So what we get is, by going every direction down an angle pi over 3, we get sort of a whole circle of points like this. But I started at this point up here and went down an angle pi over 3, but we could have started down here and gone down an angle pi over 3. That would get us to here, right? Like this, or like this. So what we get is all of these points, right? Well, this is a whole cone of points. A whole cone of points. The vertex of the cone is at the origin, and all of these points are down the same angle from the positive z-axis. So that's what that's the surface that we get if we set phi equal to a constant. I've drawn this cone as if it stops, but it doesn't. Remember, it goes up infinitely far in that direction. If your angle phi is greater than pi over 2, then right, you're going down an angle bigger than a right angle, and so your cone actually kind of flips inside out and goes down instead of up, like that. All right. So with all of this in mind, let's see if we can describe a slightly more complicated shape using polar coordinates, or I'm sorry, spherical coordinates, because of course ultimately the point of inventing spherical coordinates is to use them for triple integrals. So to be able to do that, we're going to have to be able to describe solid regions in space using spherical coordinates. So let's try this, this solid shape. So this region, its sides are a cone shape, and the top is a part of a sphere with radius 2, and the bottom, which is sort of tucked in there, the bottom is part of a sphere with radius 1. It's hard to tell from this picture, but because I didn't have a convenient way to draw it, but if you extend the sides down, they meet at a point, and the angle, sorry, not this angle here is pi over 6. Okay, so let's describe this region using spherical coordinates. So the positive z-axis, right, comes out of the origin and goes straight up like this, right? So for phi, right, we have to ask ourselves, what angles down from the positive z-axis does this region touch? Well, since the z-axis goes through this region,